Okay, we're going to go over 5 factors that affect oxygen getting into the pulmonary artery circulation from the alveolar sac point of view. We have the thickness of the membrane, surface area of the membrane, partial pressure of oxygen, ventilation perfusion ratio, and then solubility of oxygen into H2O. So the thickness of the membrane. The thicker the membrane is, the longer it's going to take for it to diffuse across it and get into circulation. That is less efficient. We see this with pulmonary edema, where that membrane is inflamed, or with pneumonia, where there's fluid that is increasing that distance in which oxygen must travel. Both of those decrease the efficiency of oxygen's diffusion into circulation. Go to the surface area of the membrane, number 2. If you have decreased surface area of that alveolar sac, the oxygen now has to pick and choose spots of efficient passageway into our circulation. Whereas if you don't, if there isn't plaques or mucus that is obstructing parts of the sac, then the oxygen can freely enter into the sac. It can hit the wall, go through the membrane, and enter circulation. Partial pressure of oxygen. Partial pressure is a combination of atmospheric pressure and then the concentration of that gas. When we go to Mount Everest, even though the concentration of oxygen is about the same as it is down at sea level, the atmospheric pressure is much less. And so therefore, there's less push of that oxygen gas from your lungs to get into your circulation. Vice versa, when you go down to sea level, there's more of a pressure. There's increased pressure for that gas in your lungs to be pushed into your blood circulation. Move over to the concentration of the gas. When we breathe in oxygen, there is an increased, there is more concentration of oxygen in the lungs than there is in the deoxygenated blood. Therefore, just based off a concentration gradient alone, areas of high concentration want to move into areas of low concentration. So oxygen moves from the area of high concentration in the lungs to the blood of low concentration. This is vice versa with the CO2. There's more CO2 in the deoxygenated blood than there is in the lungs. And so then it's able to leave the deoxygenated blood, go into the lungs, and be exhaled. An example we see this is with that VO2 max. Our body is not able to use the oxygen as quickly as we're bringing it in. Therefore, this ratio or this concentration is not what it used to be, and there's not much trafficking that goes on. There's not much movement of the oxygen into the deoxygenated blood because there's already oxygen in that supposedly deoxygenated blood. Therefore, we start to exhale increased amounts of oxygen. Ventilation perfusion ratio, number 4. This is just saying how much air or how much oxygen is getting into the alveolar sac and how much blood is getting to the alveolar sac. When we look at the aspects of location with our lungs, the upper aspects have more ventilation than perfusion. The lower aspects have more perfusion than ventilation. This is important to keep in mind with these 5 factors when we are assessing how much oxygen can diffuse into the pulmonary artery circulation just based off of where we are at in the lungs. And then lastly, the solubility of oxygen into H2O. Well, we know our blood is primarily made up of water. So it is very important for whatever gas that is entering into that circulation, it needs to be able to dissolve in that water. Especially important for oxygen, dissolve in that plasma and water so that you can hop on to hemoglobin. So even though that nitrogen makes up 78% of the atmosphere's gas and oxygen only makes up 20%, it has twice the capability to dissolve in water than that of nitrogen. And so therefore it gets into the alveolar sac, it crosses that membrane, hops into the plasma, dissolves, and is able to leap onto hemoglobin much more efficiently than the majority liter of gas in our atmosphere. And there you have it, 5 aspects of oxygen getting into pulmonary artery circulation. Have a good one.